If you walk through any American neighborhood today and look up at the rooftops, you will see one energy technology everywhere: solar panels. What you almost certainly won't see is a spiral turbine the size of a bicycle wheel turning silently, pointing itself into the wind without a motor, generating power at wind speeds that would leave a conventional turbine completely idle. It's called the Liam F1. It was developed by a Dutch inventor named Magnus Effect, who spent years asking a question that nobody in the residential wind industry had seriously answered. What if the geometry of the turbine did all the work that electronics, yaw motors, and tower height were currently doing? The result is a machine that self-orients in wind arriving from any direction, starts generating power at speeds as low as 4.5 miles per hour, produces under 48 decibels of noise at full operation, and mounts directly to a rooftop, no tower required. Independent research exists. Real field tests have been conducted, and the honest findings are more interesting than either the critics or the hype suggest. So why have almost no Americans heard of it? Let's find out. Historical origin: to understand what Effect built, you have to start 2,300 years earlier. In the 3rd century BC, the Greek mathematician Archimedes of Syracuse devised a spiral blade inside a cylinder, a device that a single operator could rotate to move enormous quantities of water uphill. The Archimedes screw became one of the most durable engineering solutions in human history, used for irrigation in Egypt, mine drainage in Rome, and water management across the ancient world. The principle was simple. A rotating spiral could move a fluid with remarkable efficiency by redirecting its kinetic energy rather than fighting it. In 2003, a Dutch inventor named Magnus Effect asked what would happen if you ran that logic in reverse. Instead of the screw moving the fluid, what if you let the fluid move the screw? Effect's insight was geometric. He observed that Archimedes had never explored the three-dimensional spiral as a rotor for energy conversion, as a shape that could redirect wind through 90 degrees and extract its kinetic energy in the process. He modeled the blade geometry after the logarithmic spiral of the nautilus shell, a form that appears throughout nature precisely because it minimizes resistance while maximizing surface contact with a moving fluid. Patent applications were filed in 2006. After years of development, field testing, and manufacturing partnerships, the turbine was named the Liam F1 after Effect's son, and the company was named the Archimedes after the mathematician whose geometry it applied. It is one of the most genuinely diarrhent approaches to small-scale residential wind energy in a generation. The science here is what actually makes this design diarrhent from every other small turbine on the market, and why those diarrhences matter specifically for American rooftops. Conventional small horizontal axis turbines, the three-blade designs you picture when someone says wind turbine, are built on lift. The same aerodynamic principle as an airplane wing. They require wind to arrive from a consistent, predictable direction at suaient speed before the pressure differential across the blade generates useful rotation. Below roughly 9 to 11 miles per hour, most small conventional turbines produce negligible power. When the wind shifts direction, a motorized yaw system must physically rotate the entire turbine head to reorient toward the new source. In the boundary layer of turbulent direction-shifting air that sits immediately above a residential rooftop, that combination of requirements is a serious problem. The Liam F1 addresses each of those problems through shape rather than electronics. The first advantage is automatic yaw. Because the conical spiral is aerodynamically balanced, the turbine orients itself into the optimal wind direction without any motor, sensor, or control system, exactly like a wind vane. The manufacturer states it responds to wind arriving at up to 60 degrees OA axis, maintaining useful rotation even when the wind is coming from well outside the turbine's primary orientation. In an urban environment where wind direction changes constantly, this eliminates the energy expenditure and mechanical stress that degrades conventional turbines. The second advantage is low cut-in speed. The Liam F1 begins generating usable power at approximately 4.5 miles per hour, The DOE's Small Wind Guidebook notes that most conventional small turbines require substantially higher wind speeds before producing meaningful output, a threshold that significantly limits their productive hours in typical suburban and urban environments. The third advantage is noise. The manufacturer states that the turbine operates consistently below 48 decibels. The DOE's own Small Wind Guidebook puts a typical 2 kW conventional turbine at approximately 55 decibels at 50 feet from the hub. The Liam spiral geometry eliminates the blade tip aerodynamic thumping that generates the characteristic noise of conventional small turbines, because the spiral has no discrete blade tips creating pressure pulses. The fourth advantage is wildlife safety. Conventional three-blade turbines rotate at high RPM, becoming a near-invisible blur that birds cannot perceive as a solid obstacle. The Liam spiral is a slow-moving, three-dimensional solid mass. The manufacturer reports no documented bird strikes across years of field deployment. The data and its honest limits. This is where the script has to be precise. Because the Liam F1 sits in an unusual position, the manufacturer's performance claims are ambitious, and independent peer-reviewed testing tells a more nuanced story. The manufacturer claims the turbine achieves approximately 80% of the BET's limit, the physical maximum any wind turbine can extract from wind, which stands at 59.3%. That would put actual efficiency at around 47%, a remarkable figure for a small residential turbine. The company states the Liam generates an average of 1,500 kilowatt-hours annually at a wind speed of 5 meters per second, roughly 11 miles per hour. To put that in American terms, the U.S. Energy Information Administration reports that the average American household consumes approximately 791 kilowatt-hours per year. At the manufacturer's stated output, a single Liam F1 at average wind conditions would cover roughly 14% of that consumption. Worth noting, the manufacturer's own literature frames this output as half a household's consumption, but that comparison is based on Dutch household usage, which is significantly lower than American averages. That framing does not apply to US buy. The independent picture is more conservative. A peer-reviewed analysis published in 2019 by Zhang et al., using a combination of computational fluid dynamics simulations, wind tunnel testing, and on-site field trials, found a maximum power coefficient of 0.293 for the Liam F1 at a wind speed of 12.7 meters per second, well below the manufacturer's efficiency claim. A broader comparative review of small wind turbines published in 2026 confirmed this finding, noting that while the Liam F1 demonstrates good aerodynamic efficiency and genuine suitability for urban environments, its performance remains below optimized lift-based turbines, and commercial deployment remains limited. The 80% BETS figure comes from the manufacturer's own documentation and wind tunnel tests. The independently verified number is closer to 50% of the BETS limit under optimal conditions, still competitive for a rooftop turbine in turbulent urban wind, but not the headline claim. What the independent research does confirm without dispute is the self-yawing behavior, the low cut in speed, and the turbine's functional stability in turbulent, multi-directional airflow conditions where conventional small turbines struggle. The villain act. So if the Liam F1 airs genuine innovations in self-orientation, low-speed operation, and noise reduction, all documented by independent research, why hasn't it reached the American mainstream? The answer has nothing to do with the physics, and everything to do with the infrastructure around. The first problem is the absence of a certified installer network. Solar photovoltaics has a mature domestic installer network in every U.S. state, standardized equipment, well-understood permitting pathways, and 2 decades of consumer familiarity. The Liam F1 has none of these. There is no certified installer network in the United States. Buyers must largely commission their own installations, which require working knowledge of charge controllers, dump load management, and roof structural assessment. That barrier alone keeps the technology out of the mainstream market. The second problem is regulation. The DOE's Small Wind Guidebook confirms that most U.S. zoning ordinances cap structure height at 35 feet, a rule written for conventional tower-mounted turbines. with no specific logic for a low-profile rooftop unit that sits within the existing building envelope. Because the regulatory framework was never written to accommodate this type of turbine, installations fall into a permitting gray area. Industry analysis has found that permitting processes for small wind in some U.S. jurisdictions extend project timelines by over 200% compared to solar installations. The third problem is economics. At a unit cost of approximately $3,200 to $7,000 before installation, depending on model and supplier, and at average American wind conditions, the payback period stretches beyond what most homeowners consider acceptable compared to solar. In high-wind coastal or elevated rural locations, parts of the Gulf Coast, the Pacific Northwest, and the Great Plains, the economics compress considerably. But those sites represent a minority of the U.S. residential market. None of this means the turbine fails to work. It means it arrived without the infrastructure needed to reach the people it was designed for. Honest limitations. This channel does not encourage you to spend money on technology that doesn't fit your situation. Here is what the research and engineering analysis actually says about the Liam F1's limit. The 80% bets limit claim is manufacturer stated and has not been replicated in independent peer-reviewed testing. The independently verified maximum power coefficient sits closer to 0.29, still respectable for a rooftop turbine, but meaningfully below the marketing headline. Anyone buying this turbine should base their financial projections on the independent figure, not the company's literature. Wind site assessment is essential. As noted in the DOE Small Wind Guidebook, wind energy scales with the cube of wind speed, meaning a site averaging 10 mph produces roughly 8 times the energy of a site averaging 5 mph. A rooftop that appears windy is not automatically a viable generation site. An anemometer should be installed at the planned mounting location for a minimum of 3 to 6 months before any investment. The Liam F1 is not a standalone power source for an American home. At the manufacturer's own stated output of 1,500 kilowatt-hours per year, it covers approximately 14% of average U.S. household consumption. It is most valuable as one component of a hybrid system paired with solar panels to extend generation into nighttime and winter months when solar underperforms. Maintenance is real. The turbine's bearings require inspection and lubrication. The manufacturer recommends visual inspection at minimum every 2 years and sells maintenance packages specifically to protect the blades and bearings. This is not a set-and-forget installation. And imitation products are a serious risk. Inexpensive spiral turbine imitations sold through mass-market online retailers have no relationship to the decade of aerodynamic development behind the genuine Liam F1 design. They typically fail within months. Practical implementation for someone who has done the wind assessment and determined their site is viable. Here is what implementation looks like. The standard Liam F1 is 1.5 meters in diameter and mounts directly to a rooftop or wall with standard hardware, rising just above the roofline rather than requiring a tower. A smaller OM 750D model at 0.75 meters diameter and approximately 32 kilograms is available for lower output OA grid and battery charging applications. Electrical integration requires a wind-specific MPP charge controller to manage variable input. A dump load, a resistor bank that dissipates excess energy as heat when batteries reach capacity, is mandatory to prevent the rotor from overspinning. Lithium iron phosphate batteries handle the variable pulsing charge profile of wind generation more reliably than lead-acid alternatives, and a battery management system is required to protect against voltage spikes. For sites where the wind assessment returns a viable average generally above 10 to 11 miles per hour, a Liam F1 paired with a south-facing solar array creates a generation profile that approaches year-round production. Solar peaks in summer daylight hours. Wind tends to strengthen in autumn and winter and generates through the night. The two profiles genuinely complement each other in a way that either system alone cannot achieve. The payoff, the Liam F1 is not a perfect product, and this channel won't tell you it is. The manufacturer's peak efficiency claims have not been independently confirmed. The installer network in America is thin. The payback period at typical wind speeds is longer than solar. But the geometry is real. The self-yawing behavior is documented. The low cut in speed is verified. The noise reduction is measurable. And the core idea that a three-dimensional spiral modeled on a 2,300-year-old mathematical principle can outperform a conventional blade in the turbulent, low-speed, multi-directional wind above an American rooftop is supported by independent research. It hasn't reached the mainstream because the infrastructure was never built around it. Not because the physics was wrong. For the right site, in the right climate, paired with solar, and integrated honestly into a hybrid system, it is one of the most interesting residential wind options available. The question isn't whether it's perfect. It's whether your roof is windy enough to find out. If this kind of honest look at real technology matters to you, subscribing and sharing is the simplest way to make sure it keeps being found.